Okay, good afternoon. I received some questions to which I want to answer. So one of them is how to derive the density for 1 or 2 dimensions. I will give one dimension here, and then you can also easily do the 2 dimensions. So for the 1 dimensions, as we did for the 3 dimensions, we start by the expression of the energy for metal, approximation for a metal, which is h squared over 8 ml. L is the dimension of the crystal, yeah, of the unit. If we look at the because it's 1 dimension, so this will be n. The axis of n, it will be 0, 1, 2, 3, etc. -1, -2, -3, etc. Okay, so we know that for each value here, there is one state. For each value, there is one state. So in total, we have n states. So if I take this, for example, so I will get the number of energy, the number of state that has an energy smaller than E3 or equal is n equal 3. So n states that have an energy smaller or equal than E. What is this energy? This energy, we just take it by isolating n here. So n squared is equal to 8ml squared of h squared E, the energy, which means that n, which is the number of energy states or level, the state that have energy less or equal than E, as I mentioned, is equal to 8ml squared over h squared 1/2 E to the power of 1/2. Okay, as I mentioned here, this is so if we want to count the number of energy states that have an energy less than 3, for example, we know that it's 3. 1, 2, 3. Okay. So now, what do we want? We want, as we mentioned before in the 3D part, we want to look at the following. This is 0. This is the number of energy state or state that have an energy less or equal than E. And I want to calculate the number of states that have an energy less or equal than E plus dE, because I want to know how many states are in this dE, and if, which is almost a continuum, and if I can calculate the number or the density in this dE, I can use it to integrate later to calculate the total number of electrons, the total number of energy states from one energy level to the other energy level, etc. So this means that this is the number of states that have an energy less or equal than E. Now, what is the number of states that have an energy less or equal than E plus dE? We use the same thing here. So this is 8ml squared h squared E plus dE 1/2. Okay. So I am interested on how many states in the band, in the small band dE. So this means that I have to do this minus this. Let's take this one as, yeah, there is a mistake here. It should be 1/2. Let's take this one as, I will put it as a constant K. Okay, let's put, just for simplicity, I will put K is equal to 8m squared h squared 1/2. Okay, so this means what I am trying to do is to do the following: to do K E plus dE to the power of 1/2 minus KE to the power of 1. This is the number of states that are or that we can find in a band DE. Now here, what I can do the Taylor expansion. Taylor expansion tells me that if I have a function fa plus h is a small value, this is approximated by fa plus h f prime of a, the first derivative. Let's apply it here. So e, a function that is e plus dE 1/2 will be equal to e 1/2 plus dE times the derivative of this. Derivative is 1/2 e to the minus 1, right? Derivative of 1/2 of x to the power of 1/2 is equal, the derivative is equal to 1/2 x minus 1. Now let's plug this here. So the number of state in DE is, again, is equal to K E half plus DE 1/2 E minus 1. This is for E plus DE minus E half. Okay, this comes from the number of states that are located below or equal to E. And you can see this will go, and the total number of the density will be 1/2 K E to the minus 1/2 dE. Now, we know that here, here, what we did, we took into account the negative values also. So we have to divide by 2 just to get rid of the negative value. So you have to multiply by 1/2 to divide by 1/2, but you also have to multiply by 2 because of the fermion, because of the exclusion principle of Pauli. So the final density of state at one dimension is equal to 1/2 that constant K e to the minus 1/2. And K, we know, K, that it's equal to the square root of 8m L squared over h squared. This is the density of states for one dimension. For 2 dimensions, you can do the same thing, except for 2 dimensions, instead of having a linear, so you will have a disk. And so you will have a disk here. And for example, if you want to find, this is n, so n will be the surface of the disk by n squared, and so on. And you can do the analysis. So this is one question. The other question is about the, I think I already solved this, is about the de Broglie wavelength. I think I already solved it. Another question came from the Fermi level for intrinsic semiconductors. We derived this, that is equal to Eg over 2 plus 3/4 kT ln mh over me. So this is the effective mass of holes, effective mass of electrons. There was one student who sent me a formula, and he said, I saw a formula about this 1/2 kT, etc. I don't know. I did not. I should use this one because we don't demonstrated this one. Another question was, which is a valid question, which was, I think during the recitation, we calculated NC and NV, but I said it at room temperature 0. No, it should be at room, sorry, at room temperature 0. No, I meant at room temperature let's say 300 Kelvin, because this has KT in there, so it will be 0. So, okay. Another question was the fact that intrinsic semiconductor, in intrinsic semiconductor, you have an I squared is equal NENH. We know in a pure intrinsic semiconductor, the number of electrons is equal to the number of holes. Okay, so this means that Ni squared is equal to Ne squared is equal to NH squared. Yeah, so you can use both of them. Sometimes when you do the calculation, you might find a slight difference, but they should be of the same order of magnitude. Okay. For example, you might find, I don't know, you might find in some calculation that Ne, for example, just to give an example, 1.5 10 to the, I don't know, 20 per cubic centimeter, and you might find NH is 1.1 10 to the 20 cubic centimeters. So yeah, so you might find this, but those are very, very similar. It's not because they are of the same order of magnitude. I'm not sure if I received other questions, but yeah, let me see, check if there is any question that just came. Yeah, if not, I will. Okay, so for the moment, I will stop here. If you have any question, just send it to me, and I will reply to it. Thank you.